Let's look at our question. Let us A be given as a closed and B is given a compact subset of a metric space. And we are going to show that the intersection is also compact. But let's observe something. A intersection B is a subset of B, which is compact. And B is compact. Hence, so closed. We can say that if a set compact, then it is closed and bound, but we are only using closed. So B is also closed, A is also closed, so A intersection B is closed. Right? Intersection of two closed sets obviously closed. And as you can see, this intersection is closed and a closed subset of a compact space. Then by definition it should be compact. And A and B is closed subset of a compact set B, so compact. This is by a theorem. I don't recall. There is no unique name. If your set is closed and subset of a compact set, then it should be also compact. So let A and B be compact subsets of a metric space. Then the union is also compact. So what should I use? What should I prove? I'm gonna prove that A union B is compact. So I'm gonna start with an open cover for this set, not A and B. Okay, that's very crucial. Answer. Let theta consisting of theta I in some index set, index class, be an open cover for the union A union B. Okay, so this cover also this will cover, and since A is subset of A union B, B is subset of A union B, and A B compact, there exist two subcovers, theta A, right? Let me index them. OE1, OEK, and theta B, OJ1, OJT, be finite subcovers for A and B respectively. Okay, so we were given a open cover for the union. Since A and B are also compact and they are inside of this union, this cover also applies for A and B also. Since A are compact, there exists a finite subcover, which are the elements are from this set. Okay, let me also point that out. This is a subclass or subset of theta. This is also subclass or subset of theta. Theta is the open cover. And we have finite subcover for A and B. If you unite them, what do you get? You get another open cover, but they both cover A union B. And clearly OA union OB, subclass of theta, is also an finite open cover for A union B, right? So the result follows. Let's look at the question. A discrete metric space XD, where the set X contains more element than any finite set. Okay, it has infinitely many elements, I mean, show that X is not compact. Okay, the K idea is X being discrete and contains more than finite elements. It's infinitely many elements. So I'm gonna construct an open cover such that it cannot be reduced to a finite subcover. It is the K idea. The K idea we are going to construct a cover, open cover theta for X such that it can not, or it can never be reduced to a finitely many open subcover, or to a finite open subcover of X. So this is my K idea. So let us construct. So theta be theta X, and the index set is the set itself. Okay, where OX is just a ball at center X with radius 1/2 X in X. So as you can see, the union of theta, or union of when X in X, OX, or just BX 1/2 is just X in X, because my metric space is discrete, and if you choose your radius is less than 1, for example in our case 1/2, this ball only consisting of X, this is only equals to X. That's why I can write this ball as like this, and this is obviously equal to X. Okay, however, this theta cannot be reduced. What do I mean? Assume to the contrary that there exists some subfamily. Let me call it F, a subfamily, a finite subfamily of F, for example X1, OX2, OXK, covers X with X equals to union of OXE, E from 1 to K. However, these are only, finitely many sets, right? This contains only Xi. So it is just equal to X1, X2, X3 to the point Xk. But it is finitely many elements, so contradiction. So it cannot, this is equal, but this cannot equal to X, because infinitely many elements this is finite. So contradiction. So my hypothesis wrong, right? So this cannot be covered by some finite set. So this discrete space is not compact. Let us give an example, or some examples for compact and non-compact curves in R2. A curve, by definition, a curve in R2 is just a function, is a function, or image, is an image of a function alpha from, you know, some interval I to R2. So this I is in R. It cannot be, yeah, it does not have to be an interval, but some subset of R, let's say. I'm talking about a general curve, not smooth, not continuous, not blah blah. Okay. So if you make some assumptions, for example, if you assume alpha is continuous or smooth, or and this I is compact, I mean it is a union of some closed intervals in R, then image of alpha is compact curve in R2. I'm not saying it is necessary condition. I'm saying just this is sufficient. Because when alpha is continuous, and if you take the image of an compact set, the image should be compact. That's why I'm using this idea. For example, let us draw something in usual topology or metric on R2. For example, this curve. Is it compact? Yes, it is compact. You need to also contain the boundaries and each point in this curve. This is a compact curve. Or a circle, for example. A circle. This is also compact. For example, some parabola, right? But it is finite parabola. This is also compact. As you can see, most of the curves, if you just restrict on some compact interval, everything is compact. Okay. But if you don't assume I is compact, what happens? Then you have the following curves. For example, in R2, an infinite parabola. Okay. For example, when function y equals x squared, this is x, this is y, and I is just real numbers, which is not compact. So if you take the image under this set R, you will get infinity parabola. So it is not compact because it is not bounded. By Henry-Borel, compact subsets of R2 or Rn are exactly closed and bounded subsets. In this case, it is not bounded, so it's not compact. Or you can consider, for example, bounded but not compact subset. For example, take the same parabola but exclude the boundaries. So you can consider I is equal to minus 2, 2. Oh, it should be open, of course. Right? So y equals to x squared. Then in this case, this curve is not compact because boundaries are not in the set. It's not closed. It is bounded, but it is not closed. It is also not compact. For example, discrete set, right? For example, in R2, if you take the natural integers on this x-axis, it is also not compact, z. And this is x-axis, and this is y-axis. This is not even a curve, but if you consider arbitrary curves, for not continuous curves, it is also a curve, okay, z. But it is not compact curve. So you can see that we can create infinitely many examples of compact and non-compact curves, but there are some examples. If you were acknowledge of some one point compactifications, we can always make some compactification of given non-compact curves. For example, if you connect these two boundaries and at some point at these boundaries, then this thing becomes a circle which is a compact. But we don't have to know this kind of things in this course. Let's look at this question. Is the set A defined by this rule? Okay, z's are defined by a function and they have some domain. Is compact or not in standard metric? First of all, let's define f of xy equals e to power x cosine y continuous on R2. Okay, of course I'm talking about standard metric or topology, the usual calculus. I mean, fine, it is continuous. So let's also look at this domain. This domain, I mean x and y's in R2 such that their absolute value sum is less or equal to 1. So geometrically it is like let me also draw this axis. Whoops. Yes, it's not good. Okay, whatever. Now this is my x-axis, this is my y-axis. Okay, then this domain geometrically determines a region on R2, right? It is my R2. So it's like the curve x plus y equals to 1. Everything is positive. Then this is the other part. This is the, so it's like a baklava, right? But you are taking this inside and boundary region. Of course, boundaries are included. Okay. This is x plus y less than 1. But there is also another way to show this is closed and bounded, right? You can define another function. Is okay. Let me do it step by step. Claim D is compact, right? First, you can see this from this picture, or you can indeed prove it, right? Define g of xy like x plus y is continuous, right? Yes, because it is sum of continuous functions, because absolute values are continuous functions, continuous, and this D is just inverse image of G with 0 and 1. So continuous, so closed. And bounded because, for example, it is inside, so D is consisting in this ball at 0, 0 with radius, let me say 1, right? If you take x and y in this region, since given x, y in D, so their summation is less than or equal to 1, and so x squared plus y squared is less than 1. Okay, this one is maybe too little. Let me make this 2. And this is also 2. Okay, because this thing can only be at maximum 1, right? This can be 1, and this is also clear from the graph, but it can be less or equal to 1, so it's correct. So x and y is in this ball 0, 0 with radius 2. It means bounded. Okay, so this D is compact because it is closed and bounded. So my original function f is also continuous, trivially, and the original question A is just the image of f on the domain D, or f of D, which is compact. F is continuous, so it is compact. So let's use the same function in the fifth question. F e to power x sin y, uniform continuous. We need to show that, or whether or it is uniform continuous or not on this region. But it is uniform convergence. Yes. Consider f on the closure of D, which is, if you recall, x plus y less or equal to 1, which is compact. As you can see, f is always on R2 continuous. So the restriction of f onto this compact set is what? Continuous. So it means that it is uniform continuous, right? Uniformly continuous. What do I mean by that? If your function is continuous on a compact set, we have used the compactness, and we have showed the compactness in the previous question, right? Of this. So it is uniformly continuous. If your function is continuous on a compact set, it is then uniformly continuous, and proof is finished. Okay, we are given a function which is continuous on R, and of course I'm talking about standard metric on R. We are going to show that this f is uniformly continuous on each bounded intervals. Okay, each bounded intervals. So f is consider the compact interval closed AB. F is also continuous on it, so f is uniform continuous on AB by a theorem. So if it is uniformly continuous on the bigger set, so it is obviously uniformly continuous on AB. So f is unif cont on AB also. The same idea, this theorem. Continuous functions on compact set is uniform continuous. Okay, let's look at the question. Let x be n be a positive sequence of real numbers with satisfying this limit. This is standard limit, just calculus. Xn minus e to power minus xn square is equal to 1 minus 1 over e. Then show that limit xn is 1. So we are going to use homeomorphism theorem in the following way. First, define fx to be x minus e to power minus x square. Okay, we are going to show this limit by step as follows. Step 1, f is increasing on 0 1 e. I want this 1 because this 1 minus 1 over e is inside of this interval, and I'm gonna use homeomorphism theorem. Step 2, f is homeomorphism on 0, 1. How so? F restricted to 0, 1. So from 0, 1 to the image F 0, 1, it is homeomorphism, is a homeomorphism by homeomorphism theorem. Since 0, 1 is compact and F is continuous and 1 to 1. Okay, so let's try then. Okay, let's in this last step EEE. So since this is homeomorphism, inverse of F is also continuous. So let me also add this. Hence, F inverse is continuous on F image 0, 1, which is consisting or contains 1 minus 1 over E. Right? No, not right, but F 1 minus 1 over E. Okay, that's correct. Now in the last step, use the definition. Use the continuity property. If G is continuous from A to B, continuous, and AN is a sequence in A with AN has limits A, then limit n goes to infinity, G of AN is equal to G of A. Okay, I'm gonna use this to show what? To show hence limit n goes to infinity F inverse, which is continuous function, F of xn, which is a sequence, goes to F inverse 1 minus 1 over E, which is in the domain. So if you calculate this limit is just limit xn, and this is just a number. But what kind of a number is that? If you calculate using this function, you get for example, let's say u this is 1. Yeah, how we can calculate it? If you put 1 in F, you get 1 minus e to the power minus 1, or 1 minus 1 over E. So this is correct. So limit xn is 1. We can use step by step. So in first step, F is increasing. Take the derivative of F with respect to x, which gives you 1 minus not 2x e to the power minus x square, which is positive, strictly positive, if x in this interval 0 and 1. Right? It is obvious. When you put 0, it is 1. When it is between 0 and 1, this is always positive, this is always positive, then everything is positive. So we have just shown that it is increasing. So F is increasing 1 to 1 on 0, 1. So let's go to the second step. F is homeomorphism on 0, 1. Which is already proven in the second step, by the way. The only thing that we need to show was this thing, and we have just shown it. In second step, we have already shown it, right? Because on 0, 1, it is increasing and 1 to 1. So by homeomorphism theorem, this is homeomorphism. So inverse is continuous on this thing, which contains this point. So this is done. Now, for any continuous function from a to b, if you have some sequence in a, and if it has a limit a n goes to a, then this happens. So we take the f inverse at each part of the limit, right, by using the given data. If you remember the data, it was my data, right? This is my f of xn. So I have limit n goes to infinity f xn equals to this point. That's why in last step 3, I can do this by using the continuity of f inverse. So result follows. Okay. If you have any question, please make some comments. So let us look at the question. Let A and B non-empty subsets of X, arbitrary metric space, where A is a closed, B is compact, with their intersection is empty. So they are just disjoint. So we are going to show that their distance between them is strictly bigger than 0. So I mean that if you have some closed subset A, if you have some compact subset B, and if their intersection is non-empty, then there is some distance, non-zero distance. Okay, so you are taking the infimum, so it is strictly bigger than 0. That's the geometric idea. That's not usually happen, right? Because when you add the boundaries, etc., there should be something, equal to 0. We don't know. We are not sure. That's why we are showing it. So how we know? How we show it? Remember, or recall, from X to R, we can define AX as DAX, and this is by definition infimum DAX, where A is from the bigger A. So is uniform continuous, right? Is uniform continuous. Or I don't even use this uniformness. Let us just say continuous. Okay, we know that, we are assuming that. Now, since B is compact, the image theta AB or DAB is also compact. Just because when you have continuous function in a compact set, the image is also compact. I only use this. And by definition, by Max-Min theorem, let me say, by Max-Min theorem, there exists some B0 in the set B, compact set B, such that this OAB is equal to OAB0, right? And this is by definition DAB0, and this is by we have just shown DAB. Now assume contrary that. Now assume to the contrary that DAB is 0, right? Because that was my point. My point was to show DAB is not 0, strictly bigger than 0. That's why I'm assuming to the contrary, because it cannot be negative, so the only choice that this thing can take is 0. So we are assuming to the contrary. Now, by definition, this is DAB B0 also. But then definition, or just some theorem that we have proven in the lectures or in the previous recitation videos, this implies B0 being in A closure. But A closure is A since A is closed. But contradiction dictates with A intersection B is empty. So it's contradiction, right? Because my sets were disjoint, but this happens, right? If you assume this, and this thing by characterization of a closure means that B0 is in the closure of A, but A is closed, so B0 is in A, so contradiction, because B0 was in the set B also. So the result follows. Now let's look at the question 10. Let X be a compact metric space. Okay, the compactness is important, so let me underline it. Metric space. And phi f be a function. Okay, we don't know it is continuous or not. It's just a function. Such that this thing happens for any xy in X, if and only if they are not equal to themselves. So we are going to show that even though f is not continuous, this function, new function, theta, defined by theta x equals to dx fx, is continuous. So let's just prove this. Okay, by using epsilon and delta. Given any epsilon, bigger than 0, let's observe the following. We want to show since my metric is standard in R, theta x minus theta x0 is less than epsilon. It's because I'm going to show for any, okay, let me call P, any P, because I'm just gonna show continuity, it's not uniform continuity. Okay, so this thing is less than epsilon. So let us open this, expand this inequality. So this is actually dx fx minus dp fp. Okay, and I know that these things are okay, and for any A, B, C, D, we have d A D minus d B C less or equal, no, strictly less, I guess, dAB minus, not plus, ACD, CD. Okay. So you can show that for any 4 points in a metric space, this thing happens. Okay. That's why instead of these, I'm just gonna replace with this. Right. So in conclusion of this observation, my OX, so OX minus OP would be less than dxp plus dfx fp. Okay, I'm just using this general inequality happens in arbitrary metric space. So I'm just gonna close this observation. By the way, before starting from epsilon, let us fix a point P. Given P in X. So our aim is to show theta is continuous at P. That's fine. This observation works. Now, how can I choose my delta? As you can see, since this would be less than delta by definition, right? And this is also satisfying the above inequality. dfxy, dfx and fy is less than xy. So this thing is less than xp, right? So this thing is less than dxp by def of f, definition of f. So what do I end up with is 2 times dxp, right, at the end. If I choose my delta to be, epsilon over 2, then everything would be fine. Now choose delta to be epsilon over 2. And if for x in x, we have dxp less than delta, let's make some space, then ox minus op, and this is by observation above less than 2 times dxp, and which is less than 2 delta, right, because of this assumption in the definition. Then this delta is just 2 epsilon over 2, which is epsilon. So it is continuous at p, for any p. Okay. Now let's show the second part. Remember the second part. Prove that there exists the one case, uniqueness is the second case, such that fx0 is x0. So we are going to show that f has unique fixed point. Okay, let's show it. I. So let me make some subtitle. Existence of fixed point x0 in x such that f x0 is equal to x0. Assume to the contrary that there is no x that's satisfying this equality. Assume to the contrary that for any x in bigger x, fx is never equal to x. Okay, now it means that this x by definition dx fx is never 0, right? It is strictly bigger than 0 for any x in x. So okay, then since x is compact, this image is strictly bigger than 0, right? So is also but first, step by step, is also compact. So there is, by definition, by def, there exists x0 in x such that O x0 is equal to image of bigger x, or infimum is not correct. This is not in the image, the maximum of the image, okay, or minimum of the image. There exists some x0 such that satisfying infimum of the images. Y is in x. Okay, so by max-min theorem, right? By def değil, not by def, by max-min theorem. Let me call by max-min theorem. Okay, so this OX0 is equal to infimum of this set. Now recall df x fy is always less than dxy, right? For any xy. This is my reminder. Now we have O f x0, which is by definition d of fx0 f x0, which is less than, by this reminder, f dx0 fx0. Okay, this is because of this property of function, and I'm just determining this is less or what. Okay, so this is less than this thing, but this thing is what? Ox0 or infimum of these images, right? Okay, so Ox0 is not an infimum of this set of y's y in x, because it is not even a lower bound, since it is not even a lower bound. Why? Because look at the inequality. My Ox0 is by definition this, and using the function property, this is bigger than this, strictly bigger, and this is by definition in the image, right? This is in this set. Ofx0 is also in this set or in this set. They are the same set. But what was my result? Ox0 was the infimum, so the biggest lower bound. But here with this inequality, it is not even a lower bound. So it is contradiction. It means that my assumption at the beginning is not correct. So there exists some x such that fx equals to x. Okay, we have just proven the existence. Now let us prove the uniqueness. Of the fixed point x0 such that fx0 is equal to x0. So how we show it? Assume that x exists x and y in x such that fx equals to x, fy equals to y. Now dxy is d fx and fy, right? By definition of this, right? X is equal to fx, y is equal to fy. That's why I can write this. But this is strictly less than dxy. This is not equal. By the definition of the function, right? By the definition of function. By the property of f. So it's a contradiction because dxy is some real number which is strictly less than itself. So contradiction. There is only one x0 such that fx0 is equal to x0. Okay, we have just proven the desired result.